Well, hello, students. It's another Sunday night, 8 o'clock. It is November 17th, the week before the Thanksgiving holiday, and it's another Mr. Rich Q&A. As I sent the email out this weekend about what we are going to talk about, I am going to spend 10 minutes on all three classes, the Algebra 2, AP Precalc, and AP Calc, giving an overview of the concepts that you should be studying this week. This really covers the St. Johns County pacing. So we'll be doing the pacing for St. John's, right? All three of those classes. So if you are in Calc, I think though you will find the things that we talk about interesting and maybe helpful to you. So stay tuned for all of it. I'm going to start with Algebra 2. And I want to talk a little bit about polynomials. I shall share my screen and we'll look at what I want to talk about with polynomials. If you've got any questions, email them to me at askmrrich@gmail.com. And let's get the share up here. And there it is. Let's get that over here. Okay. What we're studying in Algebra 2 are polynomials, and we're talking about roots of polynomials, how to factor polynomials, and how to determine their end behavior. And what I want to do is start by taking a look at a polynomial and trying to write it in its factored form so that we can find the zeros. And yeah, Izzy, you can send some questions in chat. Absolutely. So here is a polynomial, x cubed minus 6x squared plus 9x, and I want to write it in its factored form. And every time that we're trying to factor a polynomial, we're going to first see if we can factor out a GCF. And there is a GCF here that we can pull out, which is an x. So when we pull the x out, we get x squared minus 6x plus 9. And then we have a quadratic that we could pretty easily factor. And that's going to be x minus 3 times x minus 3, or x minus 3 squared. So there are two zeros to this polynomial. And notice this question was asking, what are the zeros and their multiplicity? So if you haven't learned it yet, last week, you'll see it this week, that our zeros are found by, of course, setting our y value equal to 0, solving for x. So when I set x equal to 0, I get x equals 0. Obviously, that's one of the zeros. The other zero, when I set x minus 3 squared equals 0, I get x equals 3. But we say that the multiplicity is how many times did the factor that created that 0, how many times did it appear in the factorization? Well, the x appeared once because there's an exponent of 1 on it. So this has a multiplicity of 1. The 3, however, came from x minus 3, x minus 3. It has a multiplicity of 2. Now, as far as we're concerned, what does that mean to us if we're trying to sketch the graph? Well, remember that if we know where the x-intercepts are, 0 and 3, and I plot those here on the graph, where you have an even multiplicity, a multiplicity of 2, 4, 6, that's where the function is going to be bouncing off of the x-axis at that location. If the multiplicity is odd, it will be, for that 0, it will be cutting through the x-axis at that location. Now, so what's going to happen is I do know it's going to bounce off of the 3 x-intercept. The other thing that we want to incorporate, though, into how we're going to sketch this is we do know end behavior of these polynomials. The end behavior of this particular polynomial that we're graphing, it has an odd degree and it has a positive leading coefficient. So that tells me I know what the end behaviors are going to be. The end behaviors. So it's going to go down to the left, but on the other end, on the right, it's going to be going up, because odd degreed polynomials are going to be going in opposite directions on their furthest ends, on the right and the left side. If the leading coefficient, though, was negative, it would have been opposite, and it would have been going up to the left, down to the right. But that's the behavior here, down left, up right. So when I want to sketch what this thing looks like, I know that it's going to be cutting through this 0 and then going down towards infinity, but it's going to have to turn and then bounce off of the 3. So I don't know how high it's going to go, right? But it does have to turn sufficiently so it has room to then bounce and then go in that direction. Okay. Now, I really don't know where exactly it's going to be turning, and I don't know how high it's going to go, but that probably isn't of much interest to me. This is of a lot of interest as to where this function is going to be above and below the x-axis, where it's positive and negative and where it's increasing and decreasing. So that just gives me the general shape. So factoring polynomials is extremely important. Being able to factor them into their linear factors so that you can determine the x-intercepts is what you're going to be studying this week in Algebra 2, which is also going to lead you, excuse me, to polynomial division. That's probably the main thing that you're going to be learning this week is how to divide polynomials. And you'll be using a long division method and a synthetic division method, which I am not going to go into tonight. Let's move to AP Precalc. Most of you are in 2.9 and 2.10 of AP Precalc. And what you're going to be doing in 2.9 and 2.10 is you will be rewriting, let's see, actually, I'm going to go with 2.10. I think I want to go with 2.10. What you're going to be looking at in 2.10 are going to be the fact that logarithms and exponentials are inverses of each other. And I want to grab another 2.10 to show you. I think this will be helpful. Yeah, I think this is what we want. Yep. All right. I see a few questions from Bella and Issy. Thank you for sending those. So in 2.10, really, the first thing that you're going to be looking at is how to determine whether functions would be exponential, logarithmic, or neither based on a table of discrete values. So if you take a look at, let's take a look at number one here. What's interesting about number one is it looks like the inputs are proportional, that it looks like they've been multiplied by 2. So as my outputs have equal width intervals, as I'm going up by 1 each time, my inputs are going up by a factor of 2. That right there is the absolute inverse of an exponential. Usually if it's an exponential, your outputs will be proportional. There'll be a constant multiplier while your inputs have equal width intervals. Not here, it's the opposite way around. This right here is a logarithmic. F of x is a logarithmic function. And if I gave an explanation for it, if this was a free response and they said justify that that's logarithmic, I would say, I'm not going to write it out here, but I'll speak it. As my outputs have equal width intervals, my inputs are proportional. And that is my reason as to why that's logarithmic. Then they told me that g of x is the inverse function of that. Well, you know what inverses are. You flip the x's and y's. So the outputs become the inputs, and then these inputs from f of x become the outputs on the g of x, and that makes it an exponential function. And I know that's exponential because I have equal width intervals and my outputs are proportional. All right, the other thing that you'll be taking a look at is determining whether two functions are actual inverses or not of each other. And this goes all the way back, I guess, to Algebra 2, maybe to Algebra 1, I don't remember. But the definition of two functions being inverses of each other are this, that f of g of x, when you stick one function into the other, you need to get an answer of x, but you also then need to do g of f of x and show that that also will yield an x when you simplify it. So we have to do both of those. Now, I do know there's a decent chance that they could be inverses of each other because one of them is a logarithm and one of them is an exponential. But that, of course, doesn't mean for sure that they're inverses. So the first test that we're going to try is f of g of x. So that means I'm going to put the 5 raised to the 3x. I'm going to put that in for the x right here. So this function is going to be 3 times log base 5 of, and here comes the 5 raised to the 3x power. Well, I can simplify this because I know how to simplify a log when the base of the logarithm matches the base of the exponential. These will cancel each other out. I'm using the following property of logarithms. Log base a of a raised to the b power that is just b, right? So those cancel, leaving me 3x. 3x times 3 is 9x. So I'm going to stop right there because I didn't get x, I got 9x. These are not inverses of each other. Let's do one more. Let's do this one. Let's start with f of g of x. I'm going to plug this entire function in for x right here. So this becomes 10 raised to the 5 times 1/5 log of x, like that. Well, I can go ahead and multiply the 5 times 1/5. It's 1. So this really is 10 raised to the log base 10 of x. Remember, logarithms that don't have an explicit base on them are log base 10. And I'm using this property. A raised to the log base a of b is b, because logs and exponentials cancel each other out. They are inverses of each other. This actually is x, because this is an invisible base 10. So it's x. So that checks. But now I need to check g of f of x. So I'm going to go the other way, and this x is going to be replaced with 10 to the 5x. So g of f of x would be the 1/5 times log of 10 raised to the 5x. Well, I'm using the other property that says, hey, if I have a log base 10 of 10 to the 5x, those cancel. It will leave me 1/5 times 5x, and 1/5 times 5x is x. So I have just shown that f and g in this case actually are inverses of each other. Now, I want to show you one last thing here before we move on to calculus, and that is how to find the inverse of the given function. Well, we're going to find the inverse of this exponential just like we would any other function. I'm going to swap out the y for an x, and the x's all get a y. So this thing will become x equals 3 to the y divided by 10. And this is where I'm going to use logs and exponentials as inverse functions to reverse each other, or to get rid of an exponential, I use a log, and vice versa. My variable y that I want to solve for is locked up inside of this exponential with a base 3. That means then that I'm going to use log base 3 on both sides of the equation. I am taking log base 3 on both sides. Why would I do that? Well, for good reason, because log base 3 of 3, they will cancel each other out. It strips my exponent out of the exponent, right? And makes it y over 10 is equal to log base 3 of x. And then I multiply both sides by 10, and I get 10 times log base 3 of x. And then I'll change that y to an inverse notation, inverse of h. So I just found the inverse function of 3 raised to the x over 10 power. All right. Any questions? Let me know in the chat. Oh my goodness, we got questions rolling in here. I think with all these calculus questions, we're just going to have to dive into the questions and not do the, I think we should devote the 10 minutes of calculus to calculus questions. And then I'll do one more here, and then we shall be done. So I'm going to swap my variables here. X, the y becomes an x. That's 6 times log base 5 of y. I will divide both sides by 6, leaving me log base 5 of y. But how do I get rid of a logarithm? Well, it's like we get rid of any function. I apply its inverse function. How do I get rid of a sign when I'm solving for x that's locked inside of a sign? I use arc sign. Well, the arc of a log, or the inverse of a log, is an exponential. So I'm going to raise 5 power. I was telling some students tonight, this is an algebra move that I don't think you've ever used in your algebra progression, and that is something called exponentiate. There's never been a reason to take 5 power on both sides. There is here, though, because when I raise 5 power on both sides, that's called exponentiating. What happens here is those cancel each other out. It leaves me the y, and I have 5 raised to the x over 6 And I would really write that as m inverse of x. And that's my inverse function right there. The other thing that you guys will be doing that are in AP Precalc this week is you will be getting back into graphing log functions. And that's usually not a favorite topic in Algebra 2. You did a little bit of graphing logarithm functions. You'll do a little bit more of that in 2.11. All right, so before we get into the calculus questions, next week for the St. Johns County, I just found this out today. I don't know why I didn't know this, but you guys have all of next week off, so congratulations. I will still be holding a Mr. Rich Q&A, so if you're here, great. If you're not here, that's great too. I'll be doing something here, but I will be here next Sunday night. Well, I'm going to start with some questions here. I'm going to start with, so Avery, I'm going to start with some calculus questions, and we'll get to yours here. I think should be able to get to those without too much trouble. Let me first pull up what I've got here. All right, so this question is a delta math question. So we need to do these rapid fire so we can get to as many of these as we can. Okay, so this is a delta math question here. It says, given the function that's there, f of x, determine all the intervals on which f is both increasing and concave up. Well, what we have to do to determine that is we're going to have to use the first and the second derivative. So we are going to take the first derivative and we're going to have to find our critical value. So I'm going to set it equal to 0 because I need to know where it's 0 so I can determine where it's positive and negative. So I'll pull a 9x out. So it looks like x equals 0 and x equals 8. I don't think I'm going to work the whole thing. I'm going to explain how to do it, right? So what you would do here is you would say, okay, I have critical values at 0 and 8. You are going to pick test points, -1, 1, and 9. Use the factored form to determine whether f prime of x is positive or negative in these three intervals, because where it's positive, it's increasing. Where it is negative, it's decreasing. So you can determine that. The next step is to take the second derivative. The second derivative is going to be 18x minus 72. I'm going to set that equal to 0 because the value of the second derivative tells you the concavity of the function. What is that? That is 4, I believe, right? So x is equal to 4. So then you're going to determine where is this function concave up and down. I'll pick a test point of, well, we'll just pick 3 and we'll pick 5. And I want to know f double prime sign. I don't care the value. I just want to know the sign. Same with the f prime up here. I don't care what the number is. It's just positive or negative. All right, so when x is 3, this is going to be a negative. When x is 5, that's going to be a positive. So this is concave down, less than 4. It is concave up when it's greater than 4. And you can superimpose that on here and find out where is it both concave up and increasing. Okay, so hopefully that helps there. Now I'm going to go over to do one more calc, and this comes from Taylor. That one I think was from Bella or Issy, I don't remember, but it doesn't matter. This one, see if we can get this one to come up here. Let's do this. This is another calculus question. So there's our function. What's the value of dy dx at the point 2, 2? Well, we're gonna have to implicitly take the derivative of this function. So I'm going to do that as quickly as I can. So I'm taking the derivative with respect to x. So e to the x, its derivative is e to the x. Negative y would be negative dy dx. And then on the other side of the equation, we will get, we got to use a product rule to take the derivative of this. So the derivative of the first, the derivative of x is 1 times y to the third plus the first times the derivative of the second, which would be 3y squared dy dx. Okay, here's where a lot of students will mess this up. The derivative of e squared is 0. The derivative of negative 18 is 0. Anyways, I feel like I've worked this problem before recently. But anyway, so that derivative, there's nothing to those. What I do at this point is just go ahead and throw in the X and the Y. I don't do any algebra at this point. I just throw in my Y and X values. So that's going to make that an 8. That's 4, 12. I believe that's 24, right? That'd be 2 squared is 4 times 3 is 12 times 2 is 24 dy dx. And I'll move this dy dx over and it becomes 25 times dy dx. This will become e squared minus 8. So I believe your answer is e squared minus 8 over 25. I know I'm doing that fast, but that is generally how you do it. And I can just tell you the biggest mistake, most people recognize that as 0, but students will call that like 2e to the second power. No, e squared is a constant, so its derivative is 0. All right, we're going to switch over to pre-calc for just a second, and I will pull up the next question. That's part of it right there. Let me go get the other part of it. I think this is the other part of it. Yeah, this is it. Yeah, this is the part of it here. It says the graph of f of x is given. So we are looking here at the graph of f of x, which of the following is the graph of the inverse of that function? Well, what I'm going to do here, I think, is I'm going to pick some points that I could obviously flip their x and y coordinates, right? So I'm going to be looking for a function that is passing through 10, 2, right? I'm going to flip the x and y coordinates here. I'm going to look for one that's passing through, looks like it'd be about 1, 0. And I don't know, what's another point? That point right there would look like that'd be about -7, -2, right? I'm just flipping the x and y coordinates there. So I'm looking, yeah, this doesn't make any sense that would be the inverse function. The other thing that I can do, don't forget, I can't, I'd be remiss if I didn't just say, we're looking for something that's going to be, that's probably the easier way to do that, is look for something that would be a mirror image, a reflection across the line y equals x. So if we look at these other ones, well, okay, then it's got to be this one. It's got to be D, because that would be a reflection. It looks like that's the one that would be a reflection across the line y equals x. Would it pass through 10? Yeah, it passes through 10, 2. It passes through 1, 0, it looks like, and it looks like it would pass through -7, -2, or thereabouts. Yeah, so D is our answer there. Next, I think, wait a minute. Is that, okay, let's do this one. Another calculus question. This says find the x coordinates of all relative maxima of f of x. All right, I'm going to show you a couple ways to do this. I'm going to use the first derivative test on this. So if I'm going to find places where I have relative maxima, I've got to find the critical values of the function. So I must take the derivative. So that's going to be -8x to the third minus 6x squared. And to find critical values, I'm setting that derivative equal to 0. I am now going to solve this by factoring. I will pull out a -2x, which leaves me 4x squared plus 3. No, I'm pulling an x squared out, -2x squared. And that gives me 4x plus 3. Yes, I think it does, equals 0. I'll make sure I don't mess that up. -8, if I distribute, -8x cubed minus, yeah, there we go. So then the critical values are going to be x equals 0 and x equals -3/4. Yeah, this definitely, I'm not going to do this. I was going to do the second derivative test, but I'm going to stick with the first derivative test. I think it's going to be much easier. So I'm going to stick 0 right there and -3/4 here. I'm now going to pick some test points. I pick a point to the right of 0, I'll use 1. Over here, I'm going to use a -1/2. That would be between 0 and -3/4. And then over here, I'll use x equals -1. That would be to the left of -3/4. So I'm picking these x values that represent all of the other points that are in those intervals. And what I want to know is what's the sign on the derivative of f of x. for each of those 3 test points that I picked. So I'm going to put each of these, I'm going to start with x equals -1 and put it in here. Well, when x is -1, that's going to be a negative. In fact, this is always going to be a negative because I will square it to turn it positive and then multiply by a negative. So that's going to be a negative times a negative, right? When I stick a negative right here, that's going to be a negative value. So the derivative is positive. When x is a -1/2, it's going to be a negative, right? This will always be a negative. But when this is a -1/2, that's going to be, that factor will be a positive. So my derivative will be a negative times a positive, which is a negative. When x is equal to 1, it's still going to be a negative times a positive when x is equal to the number 1, which is still negative. So therefore, this tells me the behavior of my f of x, because where the derivative is positive, it's increasing. Where it's negative, it's decreasing, and then it's still decreasing like that. And so I only have one relative max, and that is the x coordinate of -3/4 right there. Okay, that was from Bella. I hope that helped, Bella. Did I do that? -8, -6. Yeah. I don't think I messed that up, Bella. I think I got it. Okay. Next. All right, let me go over to Taylor. Okay. Yeah. Okay, so let's do, I think we got this one. All right. Let's see if I can get this one up. It's playing tricks on me here. Wait a minute. Get that out of the way. Almost got it. There we go. This tells us that h of x is 1 minus f of x over g of 3 of x. Find h prime of 2. Okay, doesn't look like much fun, but I got to find h prime of x. Got to use the quotient rule to do this. So we got to do low g of 3x times the derivative of the high. That would just be f prime of x. Low d high minus high, 1 minus f of x d low. The derivative of the bottom is g prime of 3x times 3. You can't forget the chain rule there. That would be a common mistake right there. Times 3. And then this would be all over g of 3x, the whole thing squared. Now we can find h prime of 2. I don't think I'm going to go all the way with this one, Taylor, but it would end up being g of 6 times f prime of 2 minus 1 times f of 2 times g prime of 6 times 3 all over g of 6, that whole thing squared. So the g of 6, yeah, so all of these values can come off of this. Let's make sure that nothing is undefined here. F prime of, no, so all f prime, that slope is a -1. So f prime of 2 is a -1. Let's see, g prime of 6. Yeah, g prime of 6 is going to be up here. The slope of this line segment is, I don't know, what is that slope? 1, 2, I don't know what that is. That's a slope of 1/2? No. Yeah, 1/2. Positive 1/2. Okay, so that's as far as I'm going to take it. You're just going to grab the numbers off of there, and this maybe would be one of the things that would mess students up. But you can see, right, when you're doing one of these complicated problems, you've got to be careful with the parentheses here. You've got this minus sign, but you got to be careful that you get all 3 of these quantities multiplied together with the right signs there. All right, let's go back to pre-calc. Avery had another question. I think she sent 2 questions. Let's see. Yeah, let's take a look at this one. Oh boy, I don't know about this one. This one might be too tough, but I feel like I've looked at this one before and I didn't like it, but we'll see. All right, the increasing function P gives the number of followers in thousands for a new musical group on a social media site. The table gives values of P and T and selected values of T in months since the music group created their account on this social media site. If a model is constructed, which following best applies to this situation? Well, if it is an exponential, it's got to be exponential growth. So it can't be a linear function. It can't be a linear function. And it can't be exponential decay, right? So it would have to be this function, right? Because this is, if it's exponential, well, did they tell us it's exponential? Are we supposed to figure that out? No, they just tell it's increasing. All right. So we don't really, I can't exclude those other than the fact that I see the answer, but I don't want to exclude the linear. I need to see if this is linear. So my inputs are equal width intervals. My common differences here, 10, 15, 22 and a half. Then it jumps up quite a bit. The next difference is, I don't know what that is, 30, 33, I don't know, 33 and some change. So this looks like it's not linear, right? So there's no way that I would model that with a linear function because there's not a common difference. And therefore it would have to be exponential, but it has to be exponential growth. And that looks like a 2/3 right there. So I can't pick that exponential because that would be decay. So it's got to be this one right there. So that's how I would answer that one, Avery. I wouldn't even be really trying to find what that base of the exponent is, although we could with a we could do it. Well, I think they're just assuming 3/2 that the multiplier there. Yeah, it looks like the multiplier is 1.5. Okay, so yeah, that's what it is. Okay, let's see if I had. Let me pull up the chat again. I think there's one from Issy that I didn't work yet. I think it's this one. Let's see. It looks like we're going to get through the questions. So if you've got other questions, be sure to submit them. I think we've hit these all pretty much. This says find all the intervals on which f of x is increasing. Well, the derivative is what tells us where a function is increasing or decreasing. So we need to take the derivative and set the derivative equal to 0, right? Because where the derivative is 0 is where the function would be changing possibly from increasing to decreasing, because that's where I would have a horizontal tangent line. So I'm going to take this. I don't know if I worked this one already. 4x cubed. Why does this look like I worked this one already? No, it's similar, but not the same. So there's my derivative. I do need to set this equal to 0. I'm going to solve it by factoring out 4x squared, x minus 3. Okay, so I do get x equals 0 and x equals 3. Now, I think I'm going to take this opportunity here to show you the second derivative rule for Extrema. This works really well for polynomials. So I know that I've got critical values at 0 and 3. So what I'm going to do is I'm going to take the second derivative. And the second derivative would be 12x squared minus 24x. And I'm going to evaluate the second derivative at my two critical values. F double prime of 3, excuse me, is going to be, I really just want to know whether it's positive or negative. So the second derivative, gosh, I'm going to, let's just shove it in there. So 12 times 9 minus 24 times 3. What is that? 108 minus 72. So this is positive. So what this tells me, this is called the second derivative test for relative extreme. If I find my critical values and I find a positive or negative value of the second derivative at that critical value, this tells me that the function, since the second derivative is positive, that means it's concave up, and this has to be a relative minimum. That's a relative minimum. But the problem is that when I stuck the 0 in, that critical value, into the second derivative, I got an answer of 0. So it's inconclusive and I can't use this method, right? So I really should have stuck with just doing my first derivative test. So I am going to go back to the first derivative test, which means I got my critical values 0 and 3. I'm going to pick test points to the left of 0, in between, and to the right of 3. And I'm going to determine the value of my first derivative for those 3 test points. And I'm using my factored form of my first derivative, which was 4x squared times x minus 3. Well, when x is -1, this is going to be negative. When x is 1, it's still negative. And when x is 4, it will finally turn positive. This tells me the behavior of f of x, that when the derivative was negative, it was decreasing, then it was still decreasing, and then it started to increase like that. Now, you may say, well, it's hard to picture. What does this mean? It's negative, but then the derivative was 0, and then it was negative again. Well, that's where the function is flattening out. It's coming down, flattening out at the critical value, but then it keeps decreasing, and then it reached the 3, and then it was increasing, which makes sense because this is a fourth degree polynomial with a positive leading coefficient. So that kind of behavior does make sense, or at least it's consistent with what we expect the end behaviors to be. And so the answer to this question is finding the intervals on which it's increasing. Well, there's only one interval, and it's 3 to infinity. Like that is the answer to that question. Okay, we got another one. Avery, if you're still with us, send another pre-calc. We'll have time. Here, I think this is the last question that's come through. No, Bella sent one. There you go, Bella. Way to go. But I'm gonna do Taylor's here first, and then we'll get to Bella. This question says that if h of x is equal to sine of f of x, write an equation of the line tangent to h at the point where x is equal to 1. Well, if I'm trying to get a tangent line, a line that's tangent to function h at x equals 1, it's two things I need, h of 1 and h prime of 1. I need the point of tangency, where the point and the tangent, where the where the tangent line is going to hit the function at that particular point. That's h of 1. And then I need to know the slope of that tangent line, which would be h prime of 1. So let's find h of 1. That would be sine of f of 1. Well, from that table, f of 1 is 3 pi over 4. Sine of 3 pi over 4. Well, that's over in the second quadrant, and that's going to be a positive root 2 over 2. So I know the point of tangency. It's 1 comma root 2 over 2. H prime of 1. Well, to find h prime of 1, let me find h prime of x. Well, to take the derivative of this is going to require us to use the chain rule. So that would be the derivative of sine is cosine. So that would be cosine of f of x, and then times the derivative of the inside part, which would be f prime of x. Now I'm going to find h prime of 1. That's cosine of f of 1 times f prime of 1. Okay, so f of 1 is 3 pi over 4. So it's cosine of 3 pi over 4. And whatever that is, I will be multiplying it by the square root of 2, because f prime of 1 is the square root of 2. Well, you got to know your unit circle, right? Cosine 3 pi over 4, again, over in the second quadrant, that's going to be a negative root 2 over 2. And then we're multiplying that by root 2. That looks to me like negative 2 over 2, or a negative 1 for the slope. H prime of 1. Am I missing something? I don't think so. Then what I'm going to do, I have everything I need. Over here in my point slope form, there's my x1, there's my y1. That's what we call the point of tangency, this right here. And this is my slope of the tangent line. So then the final answer here is going to be y minus square root of 2 over 2 is equal to negative 1 times x minus 1. I think that's what it was asking for, right? It was write an equation of the line tangent to h at the point where x is 1. Yeah, that's what I'm going with there. And you don't have to put that into slope intercept form. You can leave it just as is. I hope that helps, Taylor. Next. All right, Bella's question coming up. If I can get this thing to work. What is that? How does that work? Do what? Oh, wow. It lets me copy it like that. That's pretty cool. Okay. That makes things easier. I think that works. There we go. Wow. I just found a little shortcut. All right. So the graph of f prime, the derivative of f is shown below. Determine the values of x, if any, at which the function f has a local max on the interval. Okay. So you're when you get into the latter part of unit 5, I got to take a quick drink here. You're going to get to a really challenging part of this class where you have to then start making inferences about functions based on the graph of the function or its derivative or its second derivative. And it is challenging. And I'll tell you, delta math is an excellent way to drill on this. So if your teacher isn't using delta math, let me know and I'll give you access to the delta math that I've created. You need to drill like crazy on these kinds of problems to just they're totally, I don't know, they're different and you don't get good at them except through frustration and repetition. This says that I'm looking at f prime. It wants me to determine the values at which f has a local maximum on the interval from -9 to 9. Well, remember where relative extremes occur. They occur where the derivative is 0 or undefined. Here, I'm looking at where the derivative is 0. It's crossing the x-axis at -5. It's crossing it at x equals 0. And it's not crossing it, but it's touching it at 6. But I want you to think about it this way. Remember, all of these values on the y-axis, they are values of the derivative, not the function. So to the left of -5, the derivative is positive. Right? I'm just going to put a plus sign here. Now, I know this slope is negative, but I'm talking about the y values here because it's the derivative. So the derivative is positive and it switches to negative. Well, picture what's happening with f of x. If the derivative changes from positive to negative at x equals -5, right? If you were picturing what's happening on f of x, which we aren't looking at, but over here at -5, what has to be happening is the function was increasing and then it switched to decreasing because the derivative just went from positive to negative. So this is the location of a relative max. In other words, I know that where x is equal to -5, f of x has a relative max. Over here, what's happening? The derivative is crossing here, but to the left of 0, the derivative is below the x-axis, so the derivative is negative, but then it switches to be positive. So that means at x equals 0, this function f of x was decreasing, and then it changed to become increasing because the derivative just changed. So that's a place of a relative min. And this is neither a relative min or a max because the derivative is positive and then it's positive. So here's a place where the function was increasing, flattened out, and then kept increasing. So the original question here was x values where you have a local max. It would be at x equals -5. That's the answer to that question. Okay, Taylor. Yeah, I think I'll get to that one. All right. So I hope that helps, right? The common mistake is, oh yeah, relative max is right here at 2. No, no, no. That's the relative max of the first derivative, but it's asking me where f, which I'm not looking at, right? I have to make an inference about function f based on what I see on the derivative function. Okay, that is that. And then I have one more. Let's take a gander at this. Here it comes. Right. So if you're around next week, it just might be you and me. You might get all of your questions answered because I'll be here. So I don't know. I don't expect too many people to be here. Maybe I'll do it like live on YouTube, maybe. I don't know. That would be good because then you wouldn't know where I was. All right. Let's do this. So this says find dy dx for this. All right. Okay. So this is not implicit, right? This just is taking the derivative of the right-hand side. This is 1/2 tangent 3x. So that's going to be 3/2 secant squared x, right? Secant squared 3x. Oops. Secant squared of 3x. This would be minus 1 over e to the x, right? Because think about if you rewrote this, let's rewrite it in a better form. 1/2 tangent of 3x plus e to the negative x minus 2 to the x. So that makes this 3/2 secant squared 3x. That would be negative e to the minus x. All right, so how do you take the derivative of this arbitrary exponential that doesn't have e as its base? Well, that exponential is like e in that it is its own derivative. By the chain rule, the derivative of x is 1. However, when you take the derivative of an exponential that has some base other than e, you have to tack on a multiplier of the natural log of that base. So that becomes your derivative right there, Taylor. Just like that. All right. If this was, let's do a slightly different derivative of this. No, that's a bad choice of words, but like if it was negative 2 to the 3x, if you're taking the derivative of that, right, then you've got chain rule and you got this log multiplier. So it is its own derivative, right? Exponentials are in their own derivative always like that, but by the chain rule times 3, but also times the natural log of 2. That becomes the derivative right there. Let's see if anything else came through. There's like, well, we're 1 minute past, but we got started late and my next student didn't come in yet. So at least I don't think he did. He's not in this room, but anyways, I think that is it. I don't see any other questions coming through. So anyways, class, I hope this was helpful and I wish you all a great week. And if there's anything I can do to help, let me know. And those of you that are calculus students, if you want access to my Delta math practice that I have set up, let me know. I can grant you access to that with no problem at all. And you can get some extra practice. All right. It was my pleasure, Taylor. Thanks everybody for coming and submitting your questions. Happy Thanksgiving. Next week, if I don't see you, have a happy Thanksgiving next week. See you soon. Bye, everybody.